Okay, welcome back, Physics 30s, to our next lesson in Chapter 5. This is 5.3, and today we're going to be looking at the photoelectric effect and graphing. All right, so today we're going to look at how the photoelectric effect can be showed on a graph. So up here in the top left is the formula introduced in the last video for the photoelectric effect, and in this scenario we're going to be graphing EK max in joules or electron volts against frequency on the x-axis. And if we graph some data for this equation, we would get a line that looks like this. So let's start talking about some of the important pieces of information here. So first we notice that this is a straight line graph, and so that we should be able to match our photoelectric effect equation to the equation for a straight line, which is y is equal to mx plus b. And when we line these up with our y-axis being EK, showing here, and our x value being frequency, shown here on the x, we can get some information about what the slope and y-intercept represent. First off, we can see here that Planck's constant lines up with m. So our slope should represent Planck's constant, and Planck's constant is a constant, so it should be a constant value or a constant slope. So the slope of this graph should represent h of Planck's constant. Okay. The next part that we should note on the graph is the y-intercept. So b is the y-intercept, and that lines up with negative w. We can see that if I continue the graph down here, I couldn't get negative energy, so that's why my graph originally just stopped here. But if I keep that line going and see where it would interact with the y-intercept, it would interact there at a negative value, which makes sense because I have negative w here for the work function, the energy that has to be overcome to liberate that electron. So that point right there, the y-intercept, would represent our negative work function, and we saw before that this is equal to h times FO. So we can get those two pieces of information, the slope and the y-intercept. And one last piece of important information here is where the x-intercept is, or where we start this graph. This is the threshold frequency. As if I begin with 0 frequency, there's not enough energy here to liberate the electron, and I keep going, I'm still not getting any liberated electrons, but when I reach this threshold frequency, which would be at this value on the x, that's when I first start to knock electrons off, so that's the threshold frequency. Okay, so now that we understand those relationships, we're going to look at some variations. First, we're going to start with some variations where we have the same y and x values, but look at some different lines on this graph, and then we'll look at some variations with different values on the x and y. I'm going to start by showing if we had different lines on this graph. So say we had that original one from before, at least similar to before, but then it showed different lines. This would be lines for different metals, and we're going to notice some things that are similar and some things that are different. So first of all, we notice that they are all the same slope, but they are moved either left or right across the x-axis. So let's put some notes here. The slope is all the same because the slope, remember, is equal to Planck's constant. Planck's constant doesn't change for different metals, so they should all have the same slopes. Okay. Now each metal would have a different amount that they're holding on to their electrons, so they will have a different threshold frequency. So if I switch to the pen here, they will have different places where they intercept the x-axis, and this shows their different threshold frequency. The blue one has a higher threshold frequency than the green, and this kind of yellow or orange one higher than the blue. Okay. Now this also makes it so each metal has a different work function. They're kind of related, because threshold frequency required to liberate that electron, and work function is the amount of energy to liberate that electron. And so if we continued these lines, it's going to go a bit off the page, but if I continued these lines back, where they interact on the y-intercept, remember from before, that's going to be my work function, and it's going to be in the negative direction, or below the x, because we have negative w here. So that green one is going to interact first. The blue one is going to go further down to be a larger negative w value, and the orange even a larger negative w value. So as we get a higher threshold frequency, we also get a larger work function. And that's the last part, just to come up here, increase threshold frequency and increase the work function. Okay, so next we're going to look at how this graph could represent stopping voltage. So here for the equation, I've changed my EK to QV. QV is a formula for energy, and it's going to relate to the voltage that is going to be stopping this electron. So reminder that when this wave comes in from our wave source, it's going to knock electrons off of this metal. Okay, when we had the battery set up like this, and this was the negative side, and this was the positive side, electrons are going to repel from this side over here, and they're going to go over to this side, and we'd be able to measure a voltage in this circuit. But now what we're going to do is not try to increase the electron speed this way, but stop the electrons by flipping the battery around like this. Now, to determine how much voltage is required to stop the electron, we have a variable resistor here that we can move back and forth and increase and decrease the voltage. So now that negatives, or the negative side of the battery, is coming here, and I'm going to have negative on this side of the circuit. So I'll put that a little more formally here in the notes, plus on this side and minus on this side. So that means when we have our electrons in this side and we hit them with a wave and we knock the electrons off, they're going to be sent towards this side. But if this side is negative over here, it's going to feel a repulsive force. So if this electron doesn't have enough energy, it's going to get repelled and go back to this side. But if I have enough energy in my wave to knock this electron with a high enough kinetic energy to overcome that voltage, it's going to still, even though it's being repelled, still make it to the other side, and we will get a current. Okay, so if I make this voltage, okay, really high, so this negative is really negative, these are going to come back to here. Okay, but if I start decreasing this voltage to a low voltage, where this electron just makes it to this side and I just start to register a current, then I can figure out how many volts, okay, would create the amount of energy to stop that electron. So now let's put that on a graph. It's pretty similar. I've just changed, instead of having energy on the y-axis, now I have volts, okay, and that's related to energy just by volts times Q. And I'm also going to have frequency on the x, just like I did as before. And we're going to get a very similar looking graph, looking like this, being a straight line that is going to intercept the x before it reaches the y-axis. We'll have similar variables, but we'll look at how they're different in this case. So since it's a straight line, I still line up y is equal to mx plus b. H lines up with m, so I should still have a slope representing h, except for now it's going to be h over q. And you may be looking up in here and say, well, why is that h over q? Because I just had v on my y-axis, I didn't put qv on my y-axis, we have to divide by q here to cancel that out. That puts a divide by q over here. So I have h over q, and then I have f on my x-axis. So this whole part right here, I know it's getting a little bit crowded to see, but h over q is going to be my slope. So I have to add in that divided by q. Now in this rearrangement of canceling out the q over here, I also have an over q here as well. So hf over q minus w over q, that's going to affect my y-intercept. As we can see, that lines up with b. My y-intercept is now negative w over q. So when I extend to find what the y-intercept would be, again, reminder, we don't get negative volts here, but what it would be there, if I could extend that line down, you can see the y-intercept is w over q, and again, that's negative. Same as before, we can also represent w as hfo. Okay, so just the change there, both of those being over q. And the x-intercept here is still going to be the threshold frequency. The frequency being on x, as I show up top here, x is still the frequency. We haven't changed what's on the x-axis, and this is where we first start to get it coming off of that x-axis. meaning that regardless of the battery, if I have this much frequency here, I'm not going to liberate any electrons. I increase, I'm still not liberating any electrons, increase, still not liberating any electrons, and right here is the first time where I knock electrons off of that metal. Okay, and then the volts, all right, that would be required to stop this would be measured here. So first, if it's just knocked off, we just had enough frequency, say right here, to knock off those electrons, it's not going to require very many volts to stop this and send it the other way because they just got knocked off that metal. As I increase the frequency, those waves have more energy and they're going to knock the electrons on faster. I would need a higher voltage to stop them from reaching the other side. Again, then I increase the frequency higher, I would need an even higher voltage to stop that from getting to the other side of, again, this diagram. Okay, so let's look at another variation here where we change what's on the y-axis. This time we're going to put current or amps on the y-axis and frequency on the x-axis. So we're just going to recreate a mini diagram here of that photoelectric effect. It won't be too detailed, but we have this side here and we have this side here with the electrons that we're going to be shooting our waves at. Okay, so we have some electrons there and we have our wave source sending in waves. Okay, so as we first begin with a low frequency wave, which would be right here, it doesn't have enough energy to knock off the electrons. I increase it further, still not enough, further not enough, and then when I hit right here, okay, then I have enough to liberate this electron. Okay, so one photon is going to knock off one electron and it's going to go to this side. Okay, let's imagine this is happening for the green line here. So I knock off that electron and I get a current measured here. That's going to be the rate that these electrons hit this side. So I shoot a photon, knock off electron, shoot a photon, knock off electron, and it gives me a current in the circuit. Okay, as again, just sticking with the green line here, as I increase the frequency, that's going to increase the energy of this photon. Let's say that I have a increased frequency here, so it's got a smaller wavelength. Doesn't look much smaller, but hopefully you get the idea. I increase the frequency and I shoot it. It's still going to knock off one electron. It's just going to go faster to the other side. It's not going to go at a higher rate of more electrons. One photon still knocks off one electron. So my current actually just stays the same. You can't see me drawing a line there, but it's just showing like it's flat. It's staying the same. The electrons hit this side faster, but we're still knocking one electron for every photon. So that's why we have a flat line going across here. Okay, but now when I switch to the blue line, I'm not talking about blue light, I'm talking about just this blue line on the graph. That shows a different intensity. So that means if I have a higher intensity, that's saying I'm shooting more photons. So again, this line is talking about changing the intensity or the brightness, which is sending more photons. If I send more photons, I should liberate more electrons off. Right? If I send 3 photons, I should liberate 3 electrons. So I'm going to have the same required threshold frequency right here to liberate the electron, but if I'm shining a brighter light, sending more photons, once they get knocked off, I'm knocking more of them off, so I should get a higher current. And again, that will stay consistent based off the intensity. So just in some notes, after the threshold frequency, current is consistent. More intensity means more photons means more electrons liberated, and more electrons liberated means more amps because that's more charge, so more coulombs per second. And now our last variation is going to show again changing intensity of our wave that we're sending towards this metal in this mini diagram of that previous one. But now when we have current on the Y, same as that last example, we're going to have voltage on the X. And so that's relating to the voltage here, okay, that we're using to stop this. So we're going to be changing the voltage right here. And again, the more we increase it, the more it's going to repel the electrons and send them back towards this metal. So first, when I start with no voltage, okay, right here, I'm not applying any stopping voltage. I'm saying that my wave's going to come in and it's going to knock the electron off and it's going to go to this side. Okay? If I have a lower intensity, so let's say this green one here, lower intensity, I will get a lower coulomb per second or electron rate that they're coming to the other side. If I have a brighter wave, which means sending more photons, then I'm going to liberate more electrons, get a higher current. Same with intensity 3. I'm going to increase the intensity, I increase the electrons liberated, and I increase the current. Okay? So that's, I think, our first note here. With no voltage, higher intensity, more photons means more electrons reach the anode, and I have increase in current. Okay? But now as I start to move this direction along the x-axis and I start to increase the voltage, so I'm going to begin making this side negative and this side positive, right? That's going to begin to repel those electrons coming in, and we're going to get less electrons hitting this side. Now it's not 100% going to come to a right stop, because when we have the photon hit here, some electrons are going to go on a straight line, some of them might go a little bit curved, and it's going to be not 100% the same how they get knocked toward this. So those that were going off a little bit of an angle, it's almost like if we were throwing things up in the air. So imagine that I had a whole bunch of maybe like ping pong balls here, and then I'm standing on the floor, this is being the floor, and this being the ceiling. If there was no gravity and I throw them up, some are going to travel up in this direction, some are going to travel directly upwards, some are going to travel a bit to the side like this. We're going to get a little bit of a chaotic spray of these ping pong balls, right? But if there's no gravity, they're all just going to keep moving along this line and they would hit the ceiling, okay? But now if I turn gravity on, which is representing in this case turning on a voltage, then not all of them are going to reach the ceiling. As for example, this one on the edge, it had some sideways velocity, it's going to curve, and it's not going to make it all the way there. Maybe this one as well was going off to the side, it'll curve and it won't make it. So fewer electrons would make it to the ceiling if I had gravity, just kind of like fewer electrons would make it to the other side in this photoelectric experiment. So we see that the current starts to decrease here. Now, most of them are still hitting if we just apply a little voltage, and this is where the analogy to gravity kind of falls apart a bit. But if I could increase the gravity further, again, kind of trying to make an analogy to increasing the voltage over here, then these ones that were just going a bit off to the side, again, are going to fall and they wouldn't make it. They're going to fall and they wouldn't make it. But we would still be getting those that went directly there to reach the ceiling. But as I start increasing gravity, or in this case, increasing voltage, then we're going to see a downwards curve where it starts stopping more and more electrons until we reach this point, the voltage that stops all electrons. And our stopping voltage would be right here, no matter the intensity. It's stopping all of the electrons. So just in the notes, a reminder there that the reason why this is curving like that is it's the energy maximum. Not all electrons have their energy directly towards the anode, like I showed over here. So some of them will make it and some of them won't. As voltage increases, less electrons are making it to the other side. Okay, so all current stops for all intensities when Emax is not enough to get to the anode, so we've stopped all the electrons, then we have the stopping voltage right here where all electrons have been stopped. Okay, and that's it for our video for today. I hope that helped you to understand the graphing of the photoelectric effect and the different variations of graphs you can get. Let me know if you have any questions, and I will see you in the next video.